and we're going to start right away. So as you said, today we're going to talk about additive manufacturing, and I'm just going to talk about general terms in additive manufacturing. Then I'm going to go into a little bit of insight in my research here in Texas A&M University. So let's go ahead. First of all, my name is Abdelrahman Elsayed, and I am from Egypt. I have graduated with a STEM diploma in 2017 from STEM High School. Some of you might be familiar with this high school, but back then it was only one school in 6 October City, and it was for top 150 students in Egypt. After that, I came to the United States in 2017. I started my bachelor's degree in 2018. I graduated from University of Nebraska-Lincoln with a degree in mechanical engineering. While I was doing my undergrad, I had a chance to go study abroad in Singapore. So I spent 6 months or my spring semester of 2019 in Singapore at Nanyang Technological University, and I did mechanical engineering there as well. In 2021, I joined University of Texas A&M, and here I had the pleasure of studying material science and engineering, and hopefully I'll be graduating next year. So I am a little bit over half of the way done, and hopefully next year I'll be getting my PhD. I'm open for communication if you have any questions or if you'd like to talk about anything related to research or studying abroad or anything like that. Please reach out to me on my LinkedIn at Abdelrahman Elsayed AM100. So let's dig in and see what are we going to talk about today. So the agenda for today is I'm going to start with a little bit of basics of additive manufacturing, the history of additive manufacturing and the terminology in additive manufacturing. Then I'm going to talk about different categories within the additive manufacturing scope. After that, I'm going to be focusing on one technique, which is laser powder bed fusion, which is the technique, one of the most famous technique for additive manufacturing of metals, and the technique I'm doing my research on. And I'm going to be focusing on the challenges and constraints within this technique. And after that, I'm going to dive into two scopes or two applications into my research about shape memory alloys or NiTi, which is super elasticity, and then functionally graded material. So if we start with like, what is additive manufacturing? A lot of you might be familiar with the term 3D printing. Everybody might hear here and there 3D printing. And I'm pretty sure all of you have seen a 3D printer where you can see like plastic kind of wrapped into a round, and then it melts. Then there's a layer by layer deposition, which you build a part by this term of 3D printing. But 3D printing is actually, or additive manufacturing in general, is pretty old. It started in the 1977, where there's a guy whose name is Southens, who patented a direct laser way of basically melting and resolidifying the plastic by a laser. But where it really broke through is in 1986. So in 1986, there's a guy whose name is Hall, and he's from MIT. And he patented a technique called stereolithography. And this technique, which I'm going to explain a little bit about later, is basically there is a UV that can hit a resin or can hit like a photopolymer, and then it basically cross-link it and solidify it. And he was able to create a company based on his patent, which right now is one of the biggest companies in the world in the additive manufacturing with its 3D systems. Some of you might be familiar with it. Actually, fun fact, we have a printer here, laser powder bed fusion printer, and it's from 3D Systems. And then along the line, some of the key dates or key achievement for 3D printing or additive manufacturing is in 1999. It was the first time that they 3D printed organ, which was a platter back at this time. And in 2005, there was an artist in French who used 3D printing to create the first functional furniture, which was a chair. In 2010, which is not mentioned here, but in 2010, the patent for 3D printing, actually, all the patents were expired. So here in America, when you patent something, you have the key, or you have basically you are the only one who can use this technology and make money out of it. And after a certain amount of years, your patent expires. Everybody, it's basically an open source. Everybody can do it. And in 2010, there was basically the expiration of these patents, and there was a big jump in the additive manufacturing industry because everybody now can use basically these patents without. In 2017, hey everybody, I think I lost connection at some point. Can you hear me now?
We stopped right 2010 when everybody can use the 3D printing technique.
So where did you lose me? Which part?
Starting from year 2010.
Okay,
And
so I was talking about the expiration of the patents to 2010, and then there was a very or a huge jump in the industry of additive manufacturing because everybody now has the access basically to these technologies without paying the price to use them. So in 2013, there was basically a 3D printed plane that was created by University of Michigan, and it saved a baby's life. Which was amazing achievement for additive manufacturing. The biggest thing recently in 2017, Boeing basically got an FAA approval for 3D printed titanium parts for their airplane, the 787 Dreamliner, which also was amazing. So before talking about the basically the growth of AAM around the world or AM, everybody thinks, okay, is additive manufacturing is gonna replace traditional manufacturing? Is this what is the future is like? And actually, it's not true. This is not what the future looks like. So if we look at one of the techniques for conventional manufacturing, which is injection molding, we will see that injection molding at some point is way cheaper than additive manufacturing. Let's take, for example, a very simple case. Everybody of you has a phone in their hand, and they normally, when they get a phone, they get a case for it, and this case is made out of certain polymers or certain plastic. So this is like something that, for example, China produces within the millions. So the production volume of this exceed, of course, 18,000 here. So we'll see that the price for this product will be much cheaper if we use injection molding rather than using 3D printer or 3D printing or additive manufacturing. So one might ask, so when additive manufacturing is actually important is not for everything that can be done with additive manufacturing or should be done with additive manufacturing. Actually, additive manufacturing is useful for only certain application, which is when you are printing something that's basically customizable. So if you want to customize something and from one product to another, you need different customization. This where 3D printing gonna come handy. So for example, injection molding, you basically have a lot of starting costs to make the mold and to start this. But after a certain point, you have to produce the same thing over and over again, and you cannot change what you're already producing. But for 3D printing, if you have something that's need to be customized from one customer to the other, there's where 3D printing comes in handy. So the production volume for it might be huge, but it needs customization. Another thing which we can understand from this plot, if the production volume is small, if you have a need for prototype, so if you are building something or designing something and you need a couple of prototypes to test, of course you're not going to spend the amount of money to build a whole molding or get this technology of injection molding, but instead it would make more sense to actually spend the money on spend less money and 3D print these parts. As you can see here, the three lines here is basically stereolithography, fused deposition modeling, and laser sintering are three different technologies of additive manufacturing. And as we can see, the line stays constant. Despite the amount of production volume you would have, the price per unit will stay the same for technology. It wouldn't go down necessarily for additive manufacturing. On the other hand, for injection molding, as you go in production, hop in production, it goes down. So this is one thing I wanted to mention before diving in into or explaining more about additive manufacturing. That additive manufacturing is a technology that used for basically low volume production or a technology that used for something that needs to be customized. Another example for stuff that need to be customized is medical devices. Let's say like orthopedics or like human tissue replacement, stuff like this. From one person to another, you have different measurements or different things that you need to take into account, where in this case 3D printing might be the solution. So let's look at some data here of how AM have been doing economically or in the business side over the last couple of years, and how the projection are going to look like. So if you look at the graph to the right first, we're going to see that this data is only through 2020, and we can see through 2020 in the US, in the United States markets, have been about $15 billion of money, or like a market value for additive manufacturing. And this is only going up in the future. So right now, I think we are about above $20 billion in the market value for additive manufacturing. And this industry is only going up in the future. And we can see that most of this industry actually goes to functional parts. So it's not just research, or not just something that we do in like universities or research or R&D companies, but it's actually something that a lot of companies depend on to build actual functioning part. So the takeaway message from these two plots is AM, like the industry itself, is promising for the future. So if you are trying to pursue the research area, AM has the potential to be a really good area for basically growth in career-wise and economic-wise. So let's talk a little bit about the basic steps for AM processes. How do you start? You basically, AM always start at creating a model for the design. So a lot of you might have some background of like basically designing tools or designing software. So you have SolidWorks or AutoCAD or Vision or Pro, or like all of these tools right here. All of these tools, you are using them, and you basically build the design, or like this software is used to build the model of the design. After that, like when you build this design, it's not necessarily what you are building is going to be exactly the same what you are getting as an end product, but rather that you take this model and you start converting it into an STL format. An STL format is basically a format that's triangular meshes, and these triangular meshes take these 3D shapes and convert them into 2D surfaces that's closed surfaces. And this technology has been developed back in the 80s for the application of 3D printing. Once you take these STL files that has been converted from your design into these triangular meshes, you take them to your software, the printer software. And at this printer software, you are going to basically position them the way you are going to the way you want them to be printed, and slice them the way that's going to be printed. Most of 3D printing is a layer by layer deposition. Most of additive manufacturing and 3D printing, you have to be working with different slices. So your software for whatever machine you are using are going to take your STL file and start this slicing based on basically layer thickness or how thick your layer can be, and this will lead to your resolution later on. After doing that, you are gonna basically construct your physical model and let your printer to do the work. Your printer can be any one of these. It can be a powder bed, it can be a filament deposition, it can basically a polymer or resin photo polymerization. Whatever your technology is, this is the step where you actually have to let the machine does the work and construct your model. The last thing is basically post-processing. You take your model, you cut it off the substrate, you start cleaning it. If you have any support, take it off, and you end up with a final product. So that was basically the basic steps of additive manufacturing in general. That for different processes, it doesn't matter. You have to go through all of these processes. One of the things that you can bypass is creating this CAD model. Most of the time, you have to create a CAD file. But there are these cameras that can basically build a 3D file, for example, for anything using tomography scan. So this tomography scan is basically gonna take a 3D picture of something and build a CAD file for you. So you can bypass these and go ahead with your STL file created for these cameras into making. So looking at it, did you guys hear me or did you lose me again?
I have lost the connection for about 1 minute less.
Okay, where's the last part? What is the last part?
It's one of the we said about the cross boundary or cross steps.
The last step.
Yes.
So the last thing I was talking about is you can bypass this CAD model by basically doing a tomography scan. And this tomography scan is basically a camera that takes a 3D picture of one object. And by this, you don't have to create a CAD file for it. Basically, go ahead and make an STL file right away from your 3D real object. And this can be really useful for application like part replacement. Let's say one of the things that people fantasize about when they talk about 3D printing is actually for like a military application. And for a military application, imagine if you are in a battle in the other half of the world, and basically you have a broken part on one of your tanks, one of your vehicles. And instead of making an order to get it from your country, which might take weeks, you might have a 3D printer and you can take a photo of this object and then print it right away for replacement. So this is one application for 3D printing. So let's talk about the categories for additive manufacturing. There is an ASTM standard or an ISO standard that divide additive manufacturing into 7 different categories. And these different categories are binder jetting, direct energy deposition, material extrusion, and material jetting, and bar bed fusion, and sheet lamination, and that photopolymerization. And I'm gonna talk about these 7 different steps, and after that I'm gonna be focusing mainly on powder bed fusion. So let's start with the first one, which is binder jetting. So in binder jetting, it's basically you have a head that basically puts a binder or like splashes a binder over a substrate of a powder material, and then it like basically splashes one layer of powder, then you have a roller that basically feeds another layer of powder, and it's so on and so forth. You can use different materials here. It can be metals or ceramics or sands or polymers, and it can go pretty fast because you don't actually have to have only one head. You can have multiple heads, and they can finish the layer pretty fast. It's one of the fastest technique for additive manufacturing, and it's pretty funny. One of the leading companies for this technology is actually Canon's. And the reason is because these heads is the same heads you use when you actually do printing. Like normal printing, they use them to spray ink, and it's the same technology. You can use the exact same head, spread binder, and to build 3D parts. The limitation for this technique, though, is the lower mechanical properties, because when you do binder jetting, you are basically putting a glue to glue the material together. And after that, your material wouldn't be mechanically as tough for metals, for example, as your actual conventionally manufactured steel, for example. And processing is required, because if you want to take this material that's 50% or like 30% binder and 70% what your actual metal is, you need to do sintering to get rid of the binder, then to actually solidate your material together. So this was the first technique, which is binder jetting. Second technique is direct energy deposition, and it's named DED. And DED is one of the one of the most famous technologies for additive manufacturing of metals. And the way it works is basically you have basically an energy source. This energy source is mostly, or in most cases, it's a laser beam, and then you have around this energy source feeders that feed powder to this source. So as this source goes on, there's powder that gets shooted or feeded into this source, and once it touches that laser and touches your base, it basically melts and resolidifies. And it basically, this is the way it works. It can be a laser, it can be an electron beam, or sometimes a plasma arc. And this head moves basically as a welder. If any of you have seen a welder head, it can basically move in the 3 dimension. It can more than 5 or 6 axes. And the advantages or like what you can do with this is it's basically a very good tool for fixing component that already damage it, because you can mount it to like a damaged part, and then you can use it basically to melt and or like fix certain cracks and so on and so forth. The limitation for this technology, though, is it's basically have a very low accuracy since you are shooting this powder into this laser, and the surface finish whenever you are trying to build a component is terrible. In our lab, we have one of these machines. It's called Lens. It's a direct energy deposition, and it has 4 hoopers, and it can shoot 4 different types of powders in the same time. And the surface finish on these materials, it looks pretty bad. But one of the main advantages that we use this material for is, imagine if you have 4 different powders, you can start making new alloys. You can use different powders and shoot them at different rates to actually make a new alloy on the spot. So this is used for making new alloys, also used for making functionally graded parts, which I'm going to talk about later. But this is one of the famous technique for functionally grading or alloying new elements. The third technique is material extrusion. So the material extrusion is the technique that most of you are familiar with. If you have ever seen a 3D printer in your life, it's probably a 3D printer that works with material extrusion. And mostly found in offices. And the way it works, you have a material in rolls, and these materials go through a nozzle. It gets heated and then extruded into a layer. This method is really good for different type of polymers, specifically thermoplastics like PLA, ABS, and composite materials. And the advantage of it, it can be really cheap. You can basically afford it. It can go from 100 to like a couple of $100 or a couple of hundred US dollars. So it's definitely cheap compared to the other options. But the limitation for this material is it can't work with variety, or with this technique, it can't work with variety of materials. It can work for limited types of materials, and the surface finish of it is not the best. You might have seen some of these plastic 3D printed objects, and you can clearly see that there's layers that have been deposited. You can tell that this has been 3D printed. And there's another issue, or the biggest issue with this technique is the mechanical properties. So since you are putting a layer by layer, you have an isotropy in the mechanical properties. For example, if you pull in this direction, you are probably going to have less basically like less stress or less bonding, other than if you pull in the other direction, which is parallel to the direction. So this is one issue with this technique as well. The fourth technique is material jetting. So material jetting, think of it as basically a binder jetting, but instead of physically jetting the binder, you are literally jetting the material. So the way it works, you are basically shooting the material, you're depositing the material droplet by droplet, and this technique can be worked for photopolymers and wax, and it has a very, very good resolution as compared to other techniques like binder jetting or material extrusion, and it has a very good surface finish and can produce parts with different colors, as you can use different heads with different colors. And the limitation for this process is normally very slow and have a very limited materials. You cannot work with anything other than photopolymers or waxes. And it's compared, the material itself can be a little bit hard to work with and definitely more expensive than something like the material extrusion. Powder bed fusion. So this is where things gets interesting, where basically we can use a laser like we did with the DED or direct energy deposition, but then use a layer by layer deposition to build the part. So you basically center one layer, and then you deposit another layer of powder, and then center another layer. And this can work basically with a laser or electron beam. So there are 2 types of powder bed fusion. You have LBPF, then you have EPPF, which is electron beam powder bed fusion. The materials you can work with, mostly metals, but I've seen this also for polymers and ceramics. And the advantages are the surface quality, or like the surface roughness, is very, very good. And the quality of the parts can be very good. And the mechanical properties are good for end part or end user or user parts that can be used right away in applications. The limitation for this technique is basically the size, because the size of your stage or your powder bed stage is controlled how bigger you can go, and it can be slow sometimes. And working with these powders, it can be very hazardous. Why it can be hazardous? Because you are dealing with metallic powders that's basically in the size of 10 or less than 10 microns up to like 60 or 70 microns, and it can be very small. And if you freeze this powder in, it can lead to serious health issues. This technique is called sheet lamination. And basically, what you are doing is you basically combine the material into different sheets, and you are using laser to cut through these sheets the shape that you want. And this can be suitable for paper and some metals and some polymers. And it's a very low cost, very easy technique to make. But on the other side, it has limited complexity. You cannot make certain geometries with this technique. And you also have this problem of bad mechanical properties along the build directions, where these materials or these layers have been basically been like layered together previously. So the last technique is the VAT polymerization. And this was the actual or the first technique that was patented by Hall in 1986 for this for 3D printing. This is where it all started. And the idea for this technique is you have basically you have a polymer sink, and it's basically a liquid, and then you shoot a laser or a UV beam or a certain light, and when this light interacts with this polymer, it cross-links. So instead of being solid, instead of being liquid, it starts to be solid. Then you can move this stage and go to the next layer, and so on and so forth. This technique is known for a very, very good surface finish and a very good details. The accuracy and of this technique, and basically it can give you a really good part, and it can also make very complex geometries, but it's very limited to photopolymer resins, which is going to be suitable for some application, but not all applications. And the material itself can be brittle afterward. And most of the time, you take your parts and you require certain curing to get your final or end product part. So that was basically an overview of the 7 techniques for additive manufacturing. And let's go ahead and talk a little bit more about laser powder bed fusion. So as you can see here on the left, there's basically a layer deposition of powder, then scanning, then another layer deposition, and so on and so forth. And that's how it basically works. The current challenges of laser powder bed fusion, I put them into different categories. The first category is technical challenges. So the technicality here is basically there is a really bad repeatability for laser powder bed fusion. When you build certain parts and you try to recreate this part, you basically not all the time get the exact same match for these parts. There's also a problem of anisotropy management. Sometimes you have certain stresses into the part that build up while building this part, and it end up giving you a bad mechanical properties in certain areas as opposing to different other areas. Another thing is process stability. It's quite hard to determine what is your process parameters to give you a good part. So you have to find a way of basically determining what is the laser speed, what is the laser power, what is the layer thickness, all these different parameters in order to get a good part. And if you end up choosing them randomly, you might end up with a bad part. There's certain economic challenges associated with the laser powder bed fusion, which is basically it's expensive. It's very, very expensive. The machine itself, or the machine that we have a 3D system machine, which costs us is going to cost anybody, if you guys want to buy it, $500,000. So this can be very, very expensive to start with. But other than the machine itself, you have the powders. And let me break some numbers for you. For example, when I buy powders for the material I'm working with, which is nickel titanium, 1 kilogram of powder is about $1,300. So 1,300 US dollars, which is a lot for 1 kilogram. So if you want to print a certain part, you might need at least 5 kilograms. So you're talking about 6 to 7K US dollars. And this is just for one material. Other materials actually might be more expensive. And even for materials such as cheap materials such as steel, it can go as high as $300 or $400 for kilograms. So there is basically funding and investment. You need a lot of funds, a lot of investment in order to start working with these kind of technology. Also, to be able to run these machines, there are certain training and certain education. You need to undergo these trainings in order to be like able to run these machines. So the most important aspect of these is basically the material science challenges. So the additive manufacturing right now is a very, very mature technology in terms of how the laser works, how the CAD file is created, how can you design the file, how can you slice the files. All these technologies have been developing over the last 4 or 5 decades, and it's very mature now. We have a very good understanding of basically how everything works and how to make it work. But where our limitation is a material science limitation. And this is why there's a lot of research, like a lot of millions or billions of dollars getting invested into research from additive manufacturing. It's actually not a manufacturing issue anymore. It's more of a material science issue. And the reason is because there are so many aspects in material science that go into additive manufacturing. For example, powder characterization. How is your powder basically powder printable or not? And what is your powder like? What is a good powder to have? Another problem is alloy development. Which alloy are we going to be able to print, and can we create new alloys that's printable? Another problem is microstructural homogeneity. Can we actually create microstructure that can be repeatable across our print? Residual stress and distortion. Can we create a part that the way it was in the design file, the way we get it as an end part without any distortion in the part? Crack formation. Can we avoid cracking into the part? Surface roughness. Can we get a really good surface roughness in our end part? Can we get a part that have good mechanical properties and can be used as, for example, we said earlier with airplanes, Boeing airplanes? Can we get a part that's free from porosity and defects? So all of these questions are still yet to be answered with material science knowledge and material science research. So with this, I have talked basically about the challenges and the current areas that we need to research in order to work with laser powder bed fusion. Right now, I'm going to talk about one of my area of research, which is night-tie, and I'm going to be focusing on night-tie parts with superior tensile elasticity or super elasticity. So as you can see here, night-tie is an alloy which is made out of nickel and titanium, and it's called shape memory alloy. The reason it's called shape memory alloy, if you look at this graph right here, it has 3 axes. You have stress, strain, and temperature. So this material, if you apply stress to it, it's going to basically deform. But once you apply heating to it, or you start heating it up, all this deformation is going to return back the original shape. It also has this feature of being super elastic, which you can apply a lot of strain to it. And then once you release this strain, this material is going to recover back. Let's look at this like a right-left photo here. You see a hard stand. What you can see now is this material having super elastic behavior. It can super extend, as you can see here, and then it can go back to this small shape. So it goes from a very, very narrow circle to super extension. Also, this wheel here, which is a wheel that they want to use on Mars, this wheel basically can super extend. It can withstand a very, very high amount of deformation and then go back to the original shape. And this happens to something called Martinistic transformation. So in this transformation, it basically, like the atoms itself rearrange themselves to basically take that amount of strain. So this is, we call it an active material, or the shape memory alloys. and it's a very promising area of research for many applications such as aerospace or medical industry. And I just showed two examples here, but it's used for more and more applications as well, such as sensors and actuator and orthopedics and cardiovascular, as you can see here. So we want to take this material and 3D print it. But when we think about 3D printing, I talked about the current challenges, and let's look at some of these. So there are certain challenges with powder characterization, such as the powder, basically powder size distribution. As you can see here, these powders come with different sizes and come with different shapes. It can be spherical, it can be irregular, it can be broken, it can have certain porosities with them. So this is one thing to consider, is the powder itself. Then we have these material can become with different chemistry. So as you can see, as we change just 0.1 or 0.5 or 0.6% of the nickel content in this alloy, we have a different transformation behavior. It's very sensitive to the chemistry in terms of where it will be transformed. Another thing, when we print these, we end up having certain defects such as porosity, cracks, lack of fusions. These hot cracks, as you can see here, and it can basically have a very, very bad distortion or very bad burns that end up looking like this. So what we have done is, and another issue with it is the mechanical properties. As you can see, this material should withstand a very, very high amount of strains, right? But what we can see here, it basically fractured at only 5%. And in the literature, people in the past who 3D printed it, they applied 5% strain, but they were only able to get 3% transformation back. Another issue is people can't test them in tension, they test them in compression, because if you are balling in tension, all these cracks and bores are going to deform your material harder than if you are basically compressing it. You're avoiding these porosity issues because they are not going to affect mechanical. So what we have done is we build a systematic framework to create these parts, and this systematic framework contains, we start with making these single tracks. So single tracks is basically we put a layer of powder and make the laser go over them. And we see for each processing parameters, like certain powers and speed, how these tracks look like. And from these experiments, we're able to build this printability map. And this printability map, we can see that there is certain parameters along scan speed and laser and hatch spacing that can give us good prints, and other parameters can give us lack of fusions, balling, keyholing. So we now have a printability map where we can navigate where to print. And through this printability map, we are able to print cubes that basically have zero porosity. And that looks like this, looks perfect, because we have systematically decided which parameters are the good parameters to print with. After doing this, we have built a parse and we tested it mechanically in tension. And we have noticed that the oxygen content of the chamber itself have a major effect. So with higher oxygen content, oxidation happen, and then you have brittleness into your material that doesn't make it transform. But after lowering the oxygen content, we are able to get 6% strain, and then all this strain can basically be recovered back, or a good amount of it. So right now, our work stands right here. We are basically the first in the world to create a 3D printed NiTi nickel titanium that can go to 6%, can recover most of its strain back. And this work is right here compared to other work I've shown you earlier. Another thing that I want to talk about, and hopefully I can be done within the next 5 minutes, is the functionally graded NiTi. So what is functionally graded material? Some of you might have heard this terminology before. Functionally grading is you take one material and you basically change the gradient along the direction. So this is one part, you have the density here about 15%, then 60%, then 65%. So you have the density change along one part. Another thing that you can change is you can have two materials, material number A, material number B, and along the gradient, you basically mix these two materials to build a gradient from 100% A to then 100% P. We can see this at nature. So if you look at this, this is a palm tree, and this is a 3D printed concrete. So the palm tree, they have a really thick outside layer, and then they have high porosity. And this is basically a imitation of basically a palm tree through the 3D printing. So what we have noticed through printing out NiTi, that if you increase the VED, which is the amount of power or the amount of energy that you are putting, you can evaporate more nickel. So you can basically change the transformation temperature by changing the VED. And this pattern, we have seen it with different alloys, nitride and nitride hafnium. As you increase in the amount of energy, you're evaporating more nickel. So what we have decided to do is we are going to use this pattern to basically increase the VED and print a material that basically have different segments of different processing parameters. And the goal is to create a functionally graded nitride that have different amount of nickel across each gradient. And then by this, we will be able to control the mechanical behavior along these grids. And we have been able to achieve this, as you can see here, through B1 to B5 is basically these segments. And we have different transformation temperature along each one of these gradients according to the process parameters that we have used. And when we mechanically test this is where things get interesting because basically we can transform this material at different temperature. So instead of having a single transformation, we are basically having a multi-transformation where we go through certain steps to control this material. And this can be very, very useful for multiple applications. For example, let's look here at this hand. Normally for hands or for like people who lost their hands and where they have a replacement, they use different rubber or different basically SMA springs and rubber bands to control the amount of motion of their hands. But instead of having multiple springs, we can have one material which is functionally graded nitride. Through the control of temperature, we can control how much can we bend and open this material so it can move more smoothly and it can have less component through this technology. With this, I'd like to conclude my my talk, and I'd like to thank you for giving me this opportunity. And I'll be open to take questions.
Anyone who has question can raise your hand, and the mic is on, so you have the right to ask.
The question doesn't have necessarily to be about my research. If you have any question about my research, I'll be happy to answer. But if you have a general question regarding additive manufacturing in general or regarding study abroad, I'll be happy to answer any question really.
Okay, Dr. Abdelrahman, I have a question about studying abroad.
Go ahead.
How can I start studying in material science or metallurgy? How can I begin as a start?
That's a very good question, and I get this question a lot. And please feel free to reach out to me after this session, maybe through my LinkedIn. But material science right now is one of the highest researched science in the United States and in the world because of the innovations in semiconductor industry or the competition semiconductor industry. So there's a lot of opportunities here in the United States to pursue, let's say, like a higher degree, such as a master's or a PhD. What you need to do is basically you have to have an undergraduate degree. It does not necessarily have to be in material science. I myself studied mechanical engineering from my undergraduate. Then I went ahead and right now I'm doing a PhD in material science. Also, you do not need a master's to pursue a PhD. You can go ahead and start your PhD without a master's right away after your bachelor's. What you need to do is you need to work on your qualifications. What I mean by your qualifications is like your GPA, your IELTS scores, your GRE and your recommendations and your personal statement. And once you put all this stuff together, start applying to a couple or a dozen of universities, and I'm pretty sure you will find a good opportunity. My research group is very interested in hiring people from Egypt. So if you think you're a good fit or you like additive manufacturing and you want to be recruited by my group, please reach out. But you need to meet this minimum qualification in order to be considered. I hope that answers your question.
Thank you, Dr. Abdelrahman. It's clearly now.
Perfect. Also, yeah, there's I've conducted a session before, and I can send you the link later on YouTube on basically what you need to do to start applying for a PhD and what does the process look like. So I would recommend to watch this video if you are interested. I can send you the link later. Just reach out to me, and I'll be happy to help. I see there was another question. Someone raised their hands. So if there's no other questions, I'll let you take a break. I know you have another session coming up in about 10 minutes. And if you have any follow-up questions, please reach out to me. I'll be available to answer. And I would like to thank Mohammed again for inviting me to give this talk. It has been a good opportunity, and I'm very happy that I got this chance. And I'm looking forward for basically opportunities like this in the future. Thank you so much.
Thank you, Abdelrahman. It was a faithful session. We hope to collaborate again in the future, and we're happy to see you.
Absolutely. Thank you so much. You guys have a wonderful day.